Okay, before we start with today's class, let me summarize what we had done in the last class. In the last class we have noted that all the physical phenomena encountered in engineering mechanics are modeled by differential equations, and the problem addressed is too complicated to be solved by classical analytical methods. So, basically finite element method is a numerical approach by which the general differential equation can be solved in an approximate manner. So, in finite element method basically what we will be doing is we will be solving a differential equation which is valid over a domain subjected to some boundary conditions. And please note that the solution is approximate. So, basically these are the steps that are involved in solving a physical problem. First, the physical phenomena needs to be expressed in a mathematical form as a differential equation which needs to be satisfied over certain domain subjected to some boundary conditions. And this approximate solution of this differential equation we can obtain through finite element method. So, by using approximation on this, so there is using some of the methods that we will see, some of the methods which we have already seen and some of the methods that we are going to see in today's class. We are going to use some of those methods and get the finite element solutions from the given differential equation. So, in the last class we have seen how to get the governing differential equation and boundary conditions for axial deformation of bar, and this is a bar which we have taken subjected to some body force or some distributed force Q and a point load at the tip. And last time we went through the details of how we got this differential equation which needs to be valid over the domain, that is x going from 0 to L, subjected to the boundary conditions, that is displacement evaluated at x is equal to 0 is 0, displace and force at x is equal to L is 0.4 Cf. So, we need to solve this differential equation subject to these boundary conditions to solve basically this problem of axial deformation of bar. And also we noted that one of the boundary condition is essential, another boundary condition is natural. Here two boundary conditions are required because this is a second order boundary value problem, and also last class we noted a thumb rule to classify boundary conditions into essential and natural based on the order of the boundary value problem. So, for a general boundary value problem in which highest derivative present is of order 2p, the classification of boundary conditions is as follows: those boundary conditions of order 0 to p minus 1 are essential, and those boundary conditions with order p to 2p minus 1 are natural boundary conditions. So, this is how we are going to classify the boundary conditions for a general boundary value problem if no information is given about the physical information is given about the physical phenomena which that particular differential equation is representing. And as a part of approximate methods, we looked at what are these how classical solution techniques are classified. Basically these solution techniques can be classified into two categories: weighted residual methods, and in weighted residual methods the weighted residual the boundary value problem is actually we define certain measure of error in some sense, and try to minimize that error. So, the weighted residual methods work on the boundary value problem directly and try to minimize some measure of error in the solution or residual. And we looked at length some of the weighted residual methods, and also we noted that in variational methods the boundary value problem is first expressed in an equivalent variational form. The approximate solution is constructed from the variational statement, and both classes of these methods require a general form of solution to be assumed first, and this solution that we start out with can be of any form, or it can consist of function of any type that you can hope, but usually polynomial based trial solution are more preferable, or because basically they are easy to integrate and differentiate. And also if the trial solution or assumed solution, if we want to increase the order of solution, we can easily add more terms to that. So, usually polynomial based trial solutions are assumed, and one of the requirement is this assumed solution should have some unknown coefficients that needs to be determined based on the techniques that are established in each of these methods. And also we looked at length weighted residual methods. Basically weighted residual concept can be explained by taking a trial solution like this. When this trial solution is substituted into the given boundary value problem, since this is a trial solution which is approximate, the boundary value problem is not going to satisfy, or the governing equation corresponding to the boundary value problem is not going to satisfy this solution exactly. So, there will be an associated residual or error, that is the difference between left hand side and right hand side of the governing differential equation, and that residual basically in weighted residual methods we are going to multiply with a weight function and integrate over the problem domain, and that is what is defined as total residual. Total residual is this one, weight function multiplied by, or residual multiplied by weight function integrated over the problem domain. And these coefficients of the trial solution a0, a1, a2, such kind of coefficients can be, or unknown parameters can be determined by minimizing this total weighted residual. Weighted residual because we are multiplying residual with a weight function and we are integrating over the entire solution domain. So, that is why it is total weighted residual, and depending on the weight function that we select, we can categorize these weighted residual methods into three types. Some of the commonly employed weighted residual methods are least square weighted residual methods, collocation weighted residual methods, and Galerkin weighted residual methods. We looked at length each of these methods, what are the details involved in getting the approximate solution, starting with a trial solution, quadratic trial solution in the last class. So, just to summarize once again, in least square weighted residual, each of these weighted residual methods differ in the way weight function is defined. So, in least square weighted residual method, weight function is defined as partial derivative of residual with respect to the unknown parameters, and in collocation weighted residual methods, weight function is same as Dirichlet delta function, and in Galerkin weighted residual method, weight function is partial derivative of trial solution with respect to the unknown parameters or unknown coefficients. So, this is how weight functions are defined. So, once we decide what is the trial solution, or we start with a assumed polynomial based trial solution, we can actually substitute the assumed trial solution into this and try to minimize the total residual and calculate the unknown parameters or coefficients. So, to illustrate all the details of these methods, and also for comparison purposes we have selected a second order boundary value problems, solution of which we know, or the exact solution of which we know a priori. So this is the second order differential equation that we have taken, or second order boundary value problem, which needs to be solved over the domain x going from 0 to 1, subjected to the boundary conditions, and this problem can be solved exactly, and the exact solution is this one. We noted all this in the last class, and now our objective is to find approximate solution to this. So what we did in the last class is we started out with quadratic trial solution a naught plus a1x plus a2x square, and before we substitute this trial solution into the residual or into the differential equation and get the residual, we need to make sure that this trial solution is admissible trial solution. So we need to make sure that it satisfies essential boundary conditions. So basically that is what we did in the last class. We substituted the essential boundary conditions, that the two essential boundary conditions that are given for this particular problem, u evaluated at x is equal to 0 is 0, u evaluated at x is equal to 1 is 0, and substituting this we can express some of the unknown parameters in terms of others, and some of the unknown parameters can be the values can be evaluated. So substituting the boundary conditions, it turns out that a naught is equal to 1, a1 is equal to minus a2, and substituting this into the trial solution we get admissible trial solution as u is equal to a2 times minus x plus x square. And before we proceed with the weighted residual method, we require second derivative of this trial solution. After this we define what is residual, and once we have this residual, and we can multiply the weight function appropriate for the corresponding method. If it is least square method, is partial derivative of residual with respect to the unknown parameter. If it is collocation method, it is Dirichlet delta function. If it is Galerkin method, it is partial derivative of trial solution with respect to the unknown parameter, using that weight function and integrating, multiplying that weight function with this residual and integrating over the problem domain and trying to minimize. If you try to minimize the total residual, total weighted residual, we can determine what is the A2 unknown parameters in the admissible trial solution, and once we find A2, substitute back into the admissible trial solution, we are going to get this one. For least square weighted residual method, this is the solution that we obtain, starting with quadratic trial solution. For collocation weighted residual method, this is the solution that we obtained, and Galerkin weighted residual method, this is the solution that we obtained. Note that for all these methods we started with a quadratic trial solution, and we can see how this solution matches with the exact solution. Last class we have also seen a comparative plot showing comparison between exact and approximate, both the solution and derivative of solution. This is for least square weighted residual method, and collocation weighted residual method, and Galerkin weighted residual methods. So basically when we compare this least square weighted residual method, collocation weighted residual method, and Galerkin weighted residual method, the solution obtained by each of these methods, if we compare with exact, what we noticed is Galerkin weighted residual method is superior to rest of the two methods, and also even the small error that is showing up in the approximation of the weighted of the solution that is obtained using weighted Galerkin method, weighted Galerkin residual method can be improved by starting with higher order trial solution, starting with cubic or quartic or quintic trial solution, and determining the some of the coefficients using the boundary condition, rest of the unknown parameters using the minimization of the total weighted residual. So also we noted in the last class that if you see the basic Galerkin criteria, the computation of residual requires differentiating trial solution as many times as the order of highest derivative in the boundary value problem. Suppose if you are solving second order boundary value problem, we need to differentiate the trial solution for calculation of residual twice, and if you have a fourth order boundary value problem, then we need to differentiate this trial solution 4 times to evaluate this residual. So in a way we are actually imposing some restriction on the initial trial solution that we can start out for solving that particular problem. So somehow can we reduce this demand on the initial trial solution, or can we somehow reduce the order of differentiation of residual. So therefore if the basic Galerkin criteria is used directly, it would mean that we must use at least quadratic polynomial as trial solution for second order boundary value problem, and the solution for this problem is simple integration by parts. By simple integration by parts, it is possible to reduce the order of derivatives required in the trial solution. So that is the idea that is used to modify this basic Galerkin method, and when we use integration by parts, we get what is modified Galerkin method. In the last class we looked at length, what are the details, and we also noted all these points. So now coming to today's lecture, variational methods. Basically in variational methods, the boundary value problem is first expressed in an equivalent variational functional, and the approximate solution is constructed from the variational statement. Please note that for certain classes, for certain class of boundary value problem, it is possible to derive equivalent variational form, but for other sort of problems, other class of boundary value problems, it may not be possible to derive equivalent variational form. Basically equivalent variational form is written in terms of integral over the solution domain, and it is convenient for developing approximate solutions, and this integral, or in the integral over the solution domain, the trial solution is substituted and it is then minimized to get the system of equations relating the unknown parameters. So this is basically the broad outline of this procedure, and the thing is, not all problems we can solve using this, or for not all problems do not necessarily have equivalent variational form. So that is the limitation of this method, and also for some physical problems it may be possible to develop variational form from physical properties. So called energy methods of structural mechanics are based on developing functional, that is potential energy functional, and here without starting with governing differential equation, we directly use some methods to get the equivalent variational functional or potential energy functional first, and the governing differential equations can then be obtained by imposing the necessary condition for or necessary conditions for functional to be minimum. So before we proceed with the details, or to see the steps that are involved in this variational method, we need to know what is concept of variation of a function, and here the concept of variation of a function is introduced to determine how a function changes as some parameters in the function are perturbed, and variational method or Rayleigh-Ridge method is one of the variational method. So, that is why it is written in brackets Rayleigh-Ridge method. So, assume a quadratic polynomial as trial solution like this, and let us say these parameters are perturbed by a certain amount and the perturbation is a non-zero value. So, A naught is perturbed by delta A naught, A1 is perturbed by delta A1, A2 is perturbed by delta A2. So, the perturbed function is shown here, it is denoted with u tilde, and the difference between u tilde and u is what is variation of u. And if we simplify, substituting u tilde and u in the last equation, it simplifies to what is shown on the right hand side of that equation, that is variation of u is equal to delta A naught plus delta A1 x plus delta A2 x square. And variation of other functions such as first derivative of u, square of u can be written in a similar manner. This is by definition what is variation of derivative of u. Variation of derivative of u is derivative of u tilde minus derivative of u, and when we know what is u tilde when we take derivative of u tilde with respect to x, and when we take derivative of u with respect to x and substitute those two quantities into this equation, we get variation of derivative of u with respect to x as delta A1 plus 2 delta A2 x. Similarly, variation of u square is u tilde square minus u square, and substituting we can get what is variation of u square. And we noted that variation of u is delta A naught plus delta A1 x plus delta A2 x square. Please note that the coefficient of delta A naught is 1 and coefficient of delta A1 is x, coefficient of delta A2 is x square. So, with this understanding, the definition of variation can be related to the total differential, and please note that partial derivative of the trial solution that we started out with, that is u is equal to A naught plus A1 x plus A2 x square, partial derivative of u with respect to A naught is going to be 1, partial derivative of u with respect to A1 is going to be x, partial derivative of u with respect to A2 is going to be x square. So, if you see, if you substitute this information into the first equation, that is variation of u is equal to delta A naught plus delta A1 x plus delta A2 x square, coefficient of delta A naught is 1. So, I will replace 1 with partial derivative of u with respect to A naught, coefficient of delta A1 is x, replace partial derivative of u with respect to A1, replace x with partial derivative of u with respect to A1, and coefficient of delta A2 is x square, replace x square with partial derivative of u with respect to A2. Doing that, the variation of function u can be written as like this. Okay. So, this is how variation can be related to the total differential. Thus, variation of a function is equal to its total differential, and we can extend this definition to a function containing n number of parameters, and variation of that function can be written in this manner. Variation of u is equal to partial derivative of u with respect to A naught times delta A naught and so on, plus partial derivative of u with respect to an times delta an. one important point I want to infer from this equation, suppose if suppose if variation of u is equal to 0, variation of u is equal to 0 is possible only if partial derivative of u with respect to a naught, partial derivative of u with respect to a1 and so on, and partial derivative of u with respect to an are equal to or independently equal to 0. So, this is one of the important points, because this is because delta a naught, delta a1 and delta an, all these perturbed parameters are non-zero. So, if variation of u is equal to 0, it is possible that variation of u is equal to 0 only if partial derivative of u with respect to the unknown parameters or these parameters a naught to an are 0 independently. So, this is one of the important point that you should keep in mind, which we will be using later during this variational approach. And some more identities, variation of u power n times u power n minus 1, variation of u where n is integer, variation of u plus v is variation of u plus variation of v, and variation of x times u, x is not a function of any of the parameters. So, variation operator is going to operate only on u. So, x times u, and it can also be shown that the order of differentiation and integration, order of differentiation or integration and variation can be interchanged. So, the order of differentiation and variation or order of integration and variation can be changed, that is derivative of variation of u with respect to x is same as variation of derivative of u with respect to x, and similarly variation of integral x1 to x2 f x u x dx is, you can take this variation operator inside integration, and since f is not a function of any of the parameters, variation operator is going to operate only on u. And using these definitions, the following identities can easily be verified. Suppose f times variation of u is there anywhere in the derivation, we can replace that with variation of f times u because of the reasoning that we have seen earlier, that is f is independent of any of the parameters a naught a1. So, variation operator is going to operate only on u, where f is any function of x. Similarly, u times variation of u can be replaced with half variation of u square, and this definition can further be extended to the derivatives also, derivative of u with respect to x times derivative of variation of u with respect to x can be replaced with half variation of derivative of u with respect to x square whole square, sorry. So, once we are comfortable with this concept of variation of function, we can apply these some of these and get the equivalent variational functional. So, now let us go back to the boundary value problem that we are looking at. This is the boundary value problem that we are looking at, and subjected to these boundary conditions. So, here I am going to present the derivation of equivalent variational form for this particular boundary value problem. So, whatever steps we are going to look at, these steps are in general they are going to be same even for other class of problems, like these steps are applicable for any second order or fourth order or any boundary value problem. For those problems the equivalent variational functional can be obtained by following the same steps. So, the first step is multiply both sides of the differential equation by del variation of u and integrate over the domain. So, why we are multiplying here the differential equation with variation of u, because we are interested in finding the approximate solution of u. So, whichever quantity the approximate solution of which you want to find, you multiply the given differential equation with variation of that particular quantity and integrate over the domain. So, you do this on both sides. So, this is the first step, and similar to modified Galerkin method, that is the difference between Galerkin method and modified Galerkin method is incorporation of this integration by parts to reduce the highest derivative present in the equation. Same idea is used here. So, the second step is use integration by parts to reduce the order of highest derivative present in the expression to as low a degree as possible. So, this is second step. So, if you see the previous equation, we have highest derivative 2. So, we can reduce it to one order less by using integration by parts. Suppose a fourth order derivative is appearing. So, we need to use integration by parts twice to reduce it to first order derivative, because once we have fourth order, first time we use it becomes third, and second time we use second time we use integration by parts, it becomes second order differential equation again, once again third time integration by parts, we are going to get first order differential equation. So, in that manner use integration by parts to reduce the order of highest derivative present in the expression to as low degree as possible. And what is integration by parts? That is given here. Integral x1 to x2 fx derivative of g with respect to x dx can be written as fx gx evaluated within the limits x1 x2 minus integral x1 to x2 gx derivative of fx with respect to x times dx. So, this is the formula integration by parts. This we can apply on the first term, since only the first term involves second derivatives. In this case only first term involves derivatives, and thus integration did by integrating it by parts gives us this. So, substituting this back into the equation that we got in the first step, we get this equation. So, we can use some of the identities that we looked at before we started out with getting the equivalent variational functional for this particular problem. We looked at some identities, we can use those identities and simplify the first the two terms that are appearing inside the integral. So, now let us use mathematical manipulations to take the variation outside the integral. So, this is third step. Before that, using the variational identities, the first term inside the integral can be written. If you recall, we already noted one of the identities is this, and also second term inside the integral sin pi x is like fx. So, it is not function of any of the parameters. So, we can write it as variation of sin pi x times ux. So, substituting back these two terms, and also these two terms in turn they are in the form variation of u plus v, which is variation of u plus variation of v. So, we can write these two terms together in this manner. So, substituting back this information into the previous equation, substituting this expression and interchanging order of integration and variation, complete equation can be written in this manner. Basically, in this getting this equivalent variational functional or equivalent variational form for a given boundary value problem, the basic idea is to bring the given boundary value problem into the form variation of some quantity inside the bracket is equal to 0. So, if you see this equation, if we somehow get rid of first two terms, we have what is desired, that is variation of some quantity inside is equal to 0. So, the next step is use boundary conditions to simplify boundary terms. So, if you see the first two terms in this equation, they are related to boundary conditions, x is equal to 0, x is equal to 1. So, the next step is use boundary conditions to simplify boundary terms. Please note that whatever trial solution you start out with, before we substitute that trial solution into either equivalent variational functional or into the total weighted residual, we need to make sure that it is admissible trial solution. Also note that admissible trial solution satisfies essential boundary conditions, and satisfying essential boundary conditions means for any value of parameters a1, a2, an, the admissible trial solution satisfies essential boundary conditions. That means variation of u evaluated at the essential the points at which are the location at which essential boundary conditions are specified, at those locations variation of admissible trial solution is going to be 0. So, what it means, if we use admissible trial solution, variation of u evaluated at x is equal to 0 is 0, variation of u evaluated at x is equal to 1 is 0. Since here for this particular boundary value problem, two essential boundary conditions are specified, and those two boundary conditions are specified at x is equal to 0 and at x is equal to 1. Variation of admissible trial solution at x is equal to 0, at x is equal to 1, at both these points variation of u is going to be 0. So, with that reasoning we can get rid of the first two terms. So, first two terms become 0, because basically first term is variation of u evaluated at x is equal to 1 times derivative of u evaluated at x is equal to 1, and second term is variation of u evaluated at x is equal to 0 times derivative of u evaluated at x is equal to 0. So, we can get rid of these two terms based on that condition. I hope this concept is clear. So, use the boundary conditions to simplify boundary terms. So, the goal of this simplification is to express the entire expression as variation of some quantity inside the brackets is equal to 0, and with these requirements both boundary terms drop and we get this one. And now we can substitute admissible trial solution into this, and then we can use the condition that earlier we have seen when we are looking at the relationship between variation and total differential, we noted that variation of u is equal to 0 means partial derivative of u with respect to each of the unknown parameters is equal to 0. So, once we substitute admissible trial solution into this equation, last equation, everything is going to be a function of unknown parameters, and you have a function variation of that function is equal to 0, that means partial derivative of that function with respect to unknown parameters is equal to 0. So, we are going to get or we are going to determine the unknown parameters by solving those equations, that is partial derivative of that function which is in the bracket after substituting the admissible trial solution by taking partial derivative of that with respect to the unknown parameters, and we are going to get so many equations as the number of unknown parameters that needs to be determined. So, that is how we can evaluate the unknown parameters. So, one more important thing is it is not possible to bring into this form for all kinds of boundary value problems. So, that is the limitation of this variational method. And sometimes this equivalent variational functional can directly be obtained, especially for structural mechanics problems. We can use some of these so called energy methods without going through all these steps, that is step 1 to step 4 can be directly avoided by writing the equivalent variational functional using potential energy principles, or how to, if you know how to get potential energy functional based on energy methods. So, we can directly use that instead of going through all this process. If somebody gives you equivalent variational functional directly, and if you want to verify whether that equivalent variational functional is corresponding to the boundary value problem that you are looking, you can back check or you can verify by substituting the equivalent variational functional into this equation and then working in the backward direction, and we can see whether after substituting the boundary conditions we can, or substituting the condition that variation of the trial solution at the locations at which essential boundary conditions are specified is equal to 0, substituting and working backwards, all that we can, if we can verify that we can retrieve the governing differential equation of the given boundary value problem and the boundary conditions, then if we can arrive at those, then that is going to be the correct equivalent variational functional for that problem. So, that is how verification of equivalent variational functional can be performed. So, now coming back to the problem that we are looking at. So, denote the quantity inside the symbol by IU, because it is an integral. So, we can replace whatever that integral is there with some a single quantity I as a function of u. I is nothing but it is something like it is denoting that integral, and it is I is a function of trial solution u, where IU is this one. So, now let us go back to the problem. So, these are the 4 steps which are common for any boundary value problem. Once we follow these 4 steps, we can get the equivalent variational functional. Once we get equivalent variational functional, we can substitute admissible trial solution into it and minimize variation of that particular function, or we need to apply the condition variation of that potential energy functional is equal to 0. That means we need to take partial derivative of that functional with respect to the unknown parameters and solve for the unknown parameters. So, this is the boundary value problem that we are looking at subjected to these boundary conditions, and the exact solution for this problem is like this. and also we already noted for the other weighted residual methods that we already looked at. Starting with quadratic trial solution like this, after substituting the boundary conditions, u evaluated at x is equal to 0 is 0, that leads to a naught is equal to 0, u1 evaluated at x is equal to u evaluated at x is equal to 1 is 0, that leads to a1 is equal to minus a2. We already noted this, please excuse me, here there is some problem with the font. And the trial solution for the boundary value problem also we noted that this is anyway, this is this equation is correct. Trial solution is u is equal to a2 minus x plus x square. So, this trial solution, substituting this into the equivalent variational functional that we already derived, we can determine a2. Before that we need to, or I mentioned that admissible trial solution satisfies the condition that variation of u is equal to 0 at x is equal to 0 and at x is equal to 1. So, let me show you whether that is true or not. So, here I took admissible trial solution and variation of that is delta a2 times minus x plus x square. Substitute x is equal to 0 and x is equal to 1. In both cases variation of u turns out to be 0. So, the reasoning with which we cancelled out the first two terms to arrive at the equivalent variational functional, that is actually indeed it is correct or it is true. So, now thus satisfying the two requirements of equivalent functional, making the trial solution admissible. Substituting admissible trial solution into the functional, into this functional, we get this equation, and there is only one equation, sorry, we get this equation, and note that after integration the functional is reduced to a simple function of unknown parameter a2, and we want variation of that function is equal to 0. That means partial derivative of that function with respect to the unknown parameter is equal to 0. So, we get one equation and one unknown, we can solve for a2. Suppose if we have more number of unknowns, we are going to get as many number of unknowns, we are going to get as many equations as the number of unknowns that needs to be determined. Solving these equations we can determine these unknown parameters. Solving a2, solution turns out to be this one, and if you recall and if you go back and see the solution that we obtained using Galerkin method, this is exactly what we obtained using Galerkin method. And also comparison of this solution with exact solution is shown here. So, both solution and derivative of solution comparison with exact is shown in this plot. So, what we can conclude from today's lecture is, if for a particular boundary value problem we are able to find equivalent variational functional, and if we start with the same trial solution as in this case it is quadratic trial solution, and following same steps for getting admissible trial solution, substituting essential boundary conditions and reducing some of the unknown parameters or expressing some parameters in terms of other parameters. After doing all that, substituting admissible trial solution into the equivalent variational functional and minimizing functional with respect to each of the unknown parameters, we can solve for the unknown parameters, and substituting back these unknown parameters into the admissible trial solution, we are going to get the approximate solution, and whatever solution we are going to get using variational method is going to be exactly same as what we get using Galerkin method, even though the two approaches are different. But the problem with variational method is not all boundary value problems will be able to bring it to the form of variation of some quantity inside bracket is equal to 0, but if a particular problem can be brought into that form, the solution that we get using variational method is going to be same as Galerkin method.